Hello, everyone, and welcome to Processing 1 billion rows with PHP. My name is Florian. Thanks for the introduction. I'm working at Datadog, where I'm building a continuous profiler for the PHP language. So I'm somehow into internals. I'm also an open source contributor. In the, let's say, early days, I contributed to GraphQLite and PHP unit. Basically just stuff that I used in my day-to-day life, and I needed some feature, and the feature wasn't there, so I contributed it. Or I found a bug, so I fixed the bug. And nowadays, I'm more contributing to the PHP language. That's more the PHP internals book, the PHP documentation, and the PHP source code. And a year and a half ago, I became the co-maintainer of the parallel extension. Which we heard something about. Roman told you about Joe Watkins this morning. He's in a pretty bad time of his life currently. And I took over and helped him with the parallel extension. And I'm doing all of these things, although I'm married with 5 kids. So that means I have a lot of concurrency going on in my life. Okay, back to the talk. So anyone here has already heard of the 1 billion row challenge? Okay, there's just a few of you. So the mission, should you accept the challenge, is that you're going to process an input file with 1 billion rows. That's around about 10 gigabytes of data. And you're going to create an aggregated output file of that thing. And because that sounds too abstract, and we want to get into the details, and one of the details is obviously what is the input file looking. And the input file is this thing with more rows, obviously. And there is some definitions, some rules about how this file has to look like. So the first thing we have is the name of the station where a temperature was measured. The station name is defined to be a non-null UTF-8 with a minimum 1 character and a maximum 100 bytes. Then we have the semicolon, and after that, a temperature measurement. And the temperature measurement is defined to be a non-null double between minus 99.9 and plus 99.9, omitting the plus sign. And we also know that there is maximum 10,000 Unix station names in the entire file. So we don't know, it could be just those 6, but the maximum is defined with 10,000. And the output file that we should create looks something like this. Thanks to the curly braces, it feels JSON-ish. This is definitely not a JSON. The rules for the output file is it should look like this, something, have these curly braces, then the station name, and then you got to have the minimum, the average, and the maximum temperature at that station that we found. And it also has to be sorted alphabetically. And the measurements that we have, they have to be rounded to 1 fractional digit. There is more rules. This is just the input and the output file, so there's more stuff that we have to play with, or that we have to keep in play. There is no external library dependencies allowed. So it originated in the Java community, and the idea was you should not just write this in C or in assembly and then link it and then let something else do the stuff. But it should be in whatever you have, or whatever your language, your virtual machine gives you. I would go as far as say for PHP, we could bend this rule a bit because there is no native threads in PHP. And no userland threading in PHP. It's there with xparallel, but you have to install it. So I would say it's okay if we use something that's not made specifically for that purpose. Another thing is it should be 1 single source file. Basically, the idea is that we just make sure that you can read the thing. You don't need a big IDE to jump through functions where stuff is defined, but just you can read it and keep it small as possible so that people can also learn from what you did there. And this seems obvious, but it's stated the computation has to happen at runtime. There is certain things that you can do to cheat this thing. 2 things that I would like to state is, first of all, you can analyze the file. So we know some rules about it already. We know that the station name is 100 bytes, and we know that there is maximum 10,000 Unix station names. And if we analyze the file before actually computing or aggregating the data, we could find out if it's maybe in a particular order already. We can find out how many station names there are, so we can pre-allocate memory. We can find out if those stations names actually use 100 bytes or if it's just less. So we can start optimizing for these things, which we're not allowed to do. So we just have to rely on whatever file we get and pass that. And the second thing we're not allowed to do is profiler guided optimizations, which would be pretty handy here. The idea is you just write your source code in a simple way and then compile it, let it run, have a profiler observe your program, and then feed the information that the profiler observed back into the compilation step and recompile the program. And you do this over and over until you have the perfect binary for this thing, which would help, obviously, but we are not allowed to do this. So with all these rules in play, I was thinking that this was in the Java community. I saw some Ruby and Python and Go examples. I didn't see anyone doing this in PHP, so I was like, well, you should probably be able to solve this in PHP as well. So I came up with this naive solution, which is not really nice, but it's working. It solves the problem. Be with me while we go through it. So relatively easy. We need to collect the stations, so we declare just a stations array. Then open the measurements text file for reading. I'm not actually checking if the file pointer is valid. If you don't have the file there, it should probably work and just give you a warning in fget.csv because you didn't give it a resource. That's probably all you get. Otherwise, it should start reading the data. Then we're going to read the measurements line by line. Just using fget.csv. fget.csv seemed pretty handy because it has this CSV-ish thingy. You have the semicolon there, and then I'm also like, my brain is like, oh, that's a CSV. I can use fget.csv for this. We're going to read this line by line. In case the measurement that I'm reading is not existing in the array that I have, then I'm going to create an entry in the stations array with $data0 being the station name. And $data1 is the measurement. So I'm going to store this as minimum, maximum, and average. And I also store the count of measurements that I had. And in case I find the station already, I'm going to increment the counter, which we initialized with 1, and then just add the measurement to the index 2, so then later I can calculate the average. And then obviously we have to check if the measurement that we're currently processing from the file is smaller than the minimum that I have or bigger than the maximum that I have. And then store this in the $stations data 0 or 1. The data has to be sorted alphabetically, so we're going to call ksort. Ksort does sort by key, and it maintains the key value association, which is exactly what we need here. And afterwards, we can print out what we have, basically just iterating over the stations, and then also do this calculation, which does the calculation of the average temperature. You can see that I omitted just print this out, so this is just a floating point number. So we violate one rule here, and that's that we should round to one fractional digit, but I take it. In the meantime, it works. I let this script run on this computer. This is an M1 Mac. Anyone has an idea, wants to shout a number of what you think, how long this script runs, processing the 1 billion rows in minutes, days, seconds, weeks? 1 minute, okay. 20 minutes? Anyone else? An hour? Okay. So I ran the script on this computer, and it finished in 25 minutes, which was not bad. Granted that I spent, I don't know, 10 minutes writing the source code, and CPU time is cheaper than developer time, so I'll take it. I mentioned initially that I'm working at Datadog, building a continuous profiler. The profiler that we're building is a sampling profiler, so I was thinking like 25 minutes is enough. I take enough samples to actually look what it's doing. And because I'm old, that means when I started getting into computers had spinning disks, and you didn't have a disk that would store 10 gigabytes, not nearly close. So what I was thinking is, this is an I/O problem. We are not able to read 10 gigabytes of data quick into memory and process it. But actually, that's just because I'm old. Nowadays, with NVMe SSDs, this is just like this. And your operating system keeps those pages in memory anyway. So basically, you're reading against memory, not against a disk. And you can see this pretty nice here in this timeline visualization. This is from the beginning of the 25 minutes, the first 67 seconds. And we can see it's 100% CPU time. There's no idle phase, no I/O happening. This is just reading from memory and directly starts working. So non-IO problem, so I can try and look into the source code. Another visualization that you can do is the flame graph visualization. Granted, we do not have much functions, so there's not too big of a flame graph. You basically have to do these spans, the root span, and then we have one function called this fget_csv. And we can see that fget_csv accounts for 46% of the entire profile. That means that roughly half of the time that we are processing these 1 billion rows, we spend in fget_csv, just doing things. So I was wondering, maybe fget_csv was a bad choice. I wanted to find out what fget_csv is actually doing because I thought it was pretty nice. The thing is, fget_csv is built to read CSV data. What we have is actually just, it looks CSV to me because there is a semicolon in there, but it's not nearly a CSV. There is way more stuff that you can do in CSV files. You can have your enclosures and escaped enclosures and line breaks and all of these things. And fget_csv has to account for all of that. But we know from the rules that we don't have any of these problems. So I thought that maybe I can just switch to use fgets, read the line. 108 bytes seems an interesting choice, but 108 bytes is just, we have 100 bytes for the station. We know that, we know there's 1 byte for the semicolon, 5 bytes for the temperature. If it's a negative number, if it's positive, then just 4 at maximum. And then we have a 2 bytes carriage return line feed. So we're going to read 108 bytes, store this in data, and then find the semicolon with string pause, and then do substrings. Sadly, nowadays not sadly, but nowadays I'm most doing Rust. In Rust, you have these things of string slices, where you can say basically I have the string in memory, and I want to have like these 2 substrings, but I don't actually copy the data. PHP doesn't have this thing, so substring reads the string in data and creates a new string that stores in city. So there's a lot of copying going on. But anyway, I thought maybe this is a good idea because we don't need all the fget_csv stuff. So with these changes applied, not using fget_csv, but using this one, we get the runtime down to 19 minutes, 42 seconds. That's 21% less. That was really nice, and that was also the moment that got me hooked, because that was the moment I realized I can probably get way more, can get this way more down, the runtime of this entire thingy. So looking at the profile again, we see that basically we exchanged fget_csv for fget, string pause, and substring, which is the 3 functions we are calling now. We optimized for throughput, but we can see that it's nearly taking the same time as before, the same percentage amount. But we optimized for throughput, so that's okay. But what I was also interested in is this white spot here. There is something happening. That's just stuff happening in the engine, probably, stuff that PHP is doing. And I wanted to know where it's spending time. So if you switch the view to go by line mode, you start to see these 2 things here. This is actually where we interrupted the PHP engine itself and found it doing stuff. And this is line 18 and line number 23. And this is these 2 lines. Number 18 is an increment, and 23 is this comparison. And I was thinking, I looked at this a bit, I let the profile run for a while, even longer, to see more samples, but it always showed me these 2 lines. And I was thinking that this is an increment of an integer. This is one instruction on the CPU, this can't take time. Like, not time that a profiler would see. This is just like, I don't know what's happening here. And this is a comparison. Comparing 2 floating point numbers should also not be something that shows up because it should not take time. But I thought a bit about it and I found something else. This line does multiple things. It does the increment, yes, but it also does the $stations, $city thing. And this is an associative array access. So we have the $stations array with the station's name in the key. The problem, let's say, with that is that this kind of structure does not exist on a CPU. A CPU doesn't know what an associative array is. You cannot look up a memory address by giving it a string, but you have to give it a memory address. So what PHP does for us, PHP allows us to do these kind of things, but under the hood, this is baked by a hash map. So every time I do this access, PHP has to calculate the hash for $city and find the correct address in the hash map, so that it can actually get the data that we are manipulating. And the same is true below here. Probably, I thought, I don't know. But let's first try and fix this hash map access. I'm doing this all over the place. You can see everywhere there's $stations, $city, and I was like, well, maybe I can just replace all of this or most of that by using a reference. So basically in line 18, I'm doing the hash map lookup and then store the reference to the value and then just like go through it and just use the reference now. Running the script again, just with these changes, brings the runtime a bit down to 17 minutes, 48 seconds. It's 10% less. That's okay, I'll take it. It's not much, but it's okay. Another thing that I found while looking through the source code is that I'm doing more compares that I need to do. I'm doing this checking if the temperature that I'm currently reading from the file is smaller than the minimum temperature that I have for the station. But if that is the case, if the temperature is smaller, then it won't be bigger than the maximum anymore. So I can only do one comparison and then do an else if, because it could be the same, so I don't know. Yeah, just going to do it like this. One of the things here is, you can ask the question is, which comparison should we do first? This is where analyzing the file would help, but we're not allowed to do this. So I just decided to go with that and be happy. It could help if you do it the other way around, depending on if there is some kind of order in the file. But we don't know about that and we're not allowed. Rerun the script again and we are down to 70 minutes, 30 seconds. That was not a lot. Just 2%. It's better than just jitter. So if you do benchmarks, you have some jitter always. These 2% are better. You could measure them repeatedly. So I'll take it, but it's not a lot. But by looking at the source code and these comparisons, I was like, why is the comparison taking so long? This can't take too long. This is just two floating point numbers that we are comparing. And I found something else from the beginning of the PHP times. So PHP is doing type checking for us. So this, let's say trick question, we have a variable $a with the string 100 and a variable $b with the string 25.5. The question is, what will PHP do with this? Will it do an ASCII comparison or a string length comparison, or what will actually happen? PHP is pretty helpful for software developers that just start, because PHP will actually do a numeric comparison because it finds that $a and $b are numeric strings. So it will cast them to floating point and to an integer and then do a comparison and then throw the intermediate result away. Which is a problem if you remember the code, because we're doing this over and over and over again. We are reading strings and then we are doing this plus equals, where we just add to $station2, which is, this has to be converted to a floating point so that we can actually do the addition. And then we're going to do this comparison where we have to convert these to floating points, and here we have to convert to floating points again. So we're doing all of this conversion the entire time and throwing away the intermediate result because, yeah, whatever. The script works, PHP makes it working. The thing where we can help PHP is by using this typecast. Basically, when we read the temperature, we just add this float and tell PHP that whatever we get here, we get a string, obviously, but we cast that to a floating point number. And this should also help the memory footprint, because we're now not storing strings everywhere, but we're storing floating point numbers in those measurements. So we're not doing any of this type chuckling anymore. And by doing this change, we were at 70 minutes, 30 seconds. We bring the runtime down to just 30 minutes, 32 seconds. That's another 21%. That was actually pretty impressive, just by getting your types right, where you can help the engine do better decisions. So what's going on? Line 18 is still showing up. That's the array access where we do the reference. And line 23 dropped from 30-something% to 15%. And I was looking for further optimizations in the source code, and then something struck me, something that I always forget about PHP on CLI. And anyone has an idea what's so typical about PHP on CLI? Compared? Yes, no opcache. Default, no opcache on CLI. That's disabled, and with no opcache, because I have a CPU-bound problem, I have no chit. I heard people were trashing at the chit today. This is a CPU-bound problem, so it could help. I was thinking it could help. So first thing, you need opcache to have chit, so you need to set this opcache enable CLI, set this to 1, the default is 0. Then the opcache is enabled for your CLI application. And the second thing in PHP up to PHP 8.0 to 8.3, this is default enabled, but you need to give it a buffer size because the buffer size is disabled. In PHP 8.4, you need to set this to enable because it has a buffer size. So if you set both, you'll be safe in any version. And doing this, just enabling the just-in-time compiler and the op cache and running it again brings the script runtime down to 7 minutes, 19 seconds. So that's 45% down. That's pretty amazing. Then I was thinking there should be more. We should bring it down, down furthermore. The Java examples are way faster. But the Java's examples, they do one thing. They use multi-threading to take advantage of all the cores that you have in your machine. And with PHP, just with plain PHP, you don't have multi-threading in userland. But obviously, if we can somehow divide all of that problem into smaller problems and run this on multiple cores on a machine, that would be really nice, and that should yield a good impact on the problem. So I created an example. Let's see if this works. You should see my editor. Nice. Okay. Oh, it's lagging. Okay, so we had the source code and did some changes to the source code to make it work in parallel. Basically, we need to break it down into multiple smaller pieces. And the idea was that where can I like break this entire problem down to smaller pieces? Well, basically, you can say I have multiple threads, and every one of these single threads just processes a part of the file. So if I say I have 10 threads, I want 1/10 of the entire measurements text assigned to one of the threads. So Jim might say that this is a bad CLI, and it is. The CLI here is just you call it, you give it the number of threads, and if you don't give a number of threads, I'll exit. Otherwise, I cast it to an integer, so whatever you gave, it's hopefully something that I can work with. That's the entire CLI interface. Then I wrote this function to get the file chunks. So what the get file chunks basically does is you give it the file name to the measurements text, and you give it the number of CPUs, so the number of parallel threads that you want to have. Because this is CPU bound, we should not allocate more threads than we have physical CPUs, because otherwise the operating system would just switch between threads all the time, because you're working on all of them. So this get file chunk functions gets the file size, which is roughly 10 gigabytes. Then we find out how big the chunks have to be. Just divide that by the CPU count, so we know if you have to process a gigabyte, 1.5 gigabytes, something like that. Then open the file, and then we need to find all the chunk boundaries. So we need to say you're processing from this line to this line to this line to this line, and so on. So this is basically what's happening here. So I'm iterating over the file. I'm going to calculate the minimum position. So I have the chunk end for the first chunk. Then we're going to seek to the position of where the chunk should end. And then we're going to do an fgets. Fgets is I'm not interested in the return, in the data that fgets returns. I'm just interested in the side effect of fgets moving the file pointer to the end of the line. That's all it does. So the fseek is basically seek to some position in the file, and then fgets is forward to the next carriage return line feed. Then I'm going to use ftell to get the file position and have my chunk end. And then we're going to store this in this array and iterate over the entire file until we are finished, until we reach the end of the file. And then have all of these chunk start, chunk end, which is just byte offsets into the file. And then be polite and close the file, and then return the chunks to whoever called us. This is the function that does the processing. We've seen all of this already in these slides. The difference here is that I have the chunk start now. So in the beginning, I'm going to open the file, then seek to the chunk start, which is the thing this thread should actually work on. And then we need to have another exit condition. The exit condition is now not that fgets doesn't read any data anymore. The exit condition is now we reached our end of the chunk, and then we break and jump out. And the rest here is just exactly the same. So this function, if it's run in a thread, will just process one chunk and then return an intermediate result in the stations. And then we need to combine all of them later. The magic comes here of starting the threads. So I'm going to call get file chunks. So I have the chunks, I have the this futures array. And then we're going to iterate over the threads count. So if you started, say, 10 threads, 20 threads, whatever, it will iterate over this. It will just iterate over this and spawn 20 new threads. And it does so by calling the parallel run function. And the parallel run function, you give it a closure to something that it should execute in this other thread. And you give it the arguments of what it should give there. And that's the file name and the chunk start and end for this that this thread should process. And the parallel run function gives us back, relatively immediately returns a future, which is an object that we can use to communicate to the thread. So we could send data to this. We could wait. We could ask it if the process or the thread is already finished. And once it's finished, we can request the return value. So whatever return that closure had, we can request that. And then we are like. Then in the meantime, those threads are running, and then we start iterating over the threads count again. We're going to call this value function the future that we got. The $futures array has 10, 12, 20 futures, and the value function on the future will block until that thread is finished and has done a return. So whenever that thread has done the processing all the aggregated data, they give us the intermediate return, the intermediate value back, and the value function returns that into the chunk result. And then we need to combine the intermediate results that we get from each thread into the one big measurements array. And once we have that, it starts to looking familiar again. Just do case sort and echo out the thing. So I ran this, and it was faster. But I need to go back to these slides. Yes. I ran it, and it was actually way faster. It was 1 minute and 35 seconds. This was a lot. But in the moment I ran this, I found out, I remembered something. So I'm working on the profiler. The profiler is basically a PHP extension. So every time something is weird or I need to find out something, I want a PHP version that is not optimized and has debug symbols in it. So my PHP version that I'm running locally has these C flags. So if you compile software in C, you have these C flags where you can tell the compiler that it should do optimizations or not or whatever. I'm using these C flags to have debug symbols. So I know all the symbols that are in there. I have a lot of debug information in there, so I can debug the PHP process way easier. And I say it the compiler should not do any optimizations. No inlining, no loop unrolling, no whatever. This is a problem because this means that the PHP binary that I was running all the benchmarks the entire time was a debug build, which is not supposed to be fast. It's supposed to have a lot of debug information. So I recompiled with, removed the -g, and I opted for -os. The default, I think the Docker container I built with -o2. S is basically the same, only that it also enables optimization for size to keep the binary size small. So after I did that, I run it again, and this time I can actually run it here. Let's go out. And I have 12 cores in this machine, so we're going to run it with 12 cores, and then we see, hopefully we see how quickly it is, and hopefully it's faster than 1 minute 35 seconds. Tension. Come on, do your thing. Okay, it's done. This is just the end of the list, and it took 27 seconds, which is pretty awesome. Okay, let's go back to the slides. So I run the script, and it clocked in at 27.7 seconds. Coming from 25 minutes, that was awesome, but the Java was still faster, so I wanted to have a look again. The profiler recorded I looked at the profiler again and let it record what's going on. And you can see all these threads are working. All of these threads with the blue lines is the worker threads, which are actually reading the data and doing all the work. The last thread here, this is the main thread. So you can see the initial, this is one dot, meaning there is, it took the sampling profiler took one sample, and in the end it took also one sample. This is at maximum 10 milliseconds. So that means the entire process spends 20 milliseconds or 10 milliseconds, at maximum 10 milliseconds in the beginning with calculating the chunks. And then in the end, with combining the intermediate results, also around about 10 milliseconds. So this is not something to look for optimization. The problem still lies in this entire thing, reading the data, number crunching through all of that. You can also see there's a slightly, like the last thread is quicker than the others, which is just because in calculating the chunks, I always forward to the next. So the last chunk is the smallest. So this one is there first. But still, you can still see there's 12 threads, or I think this is 10 threads reading data from a file. This is still not an I/O problem. You can still see CPU time 100%. There is no I/O wait happening, so this is still not an I/O problem, even if you're reading a lot of stuff. So once I had this done, I wrote a blog post about this, and people showed up, were interested about this, and one guy showed up, and he was like, I have a few other ideas that we should try out. So we tried out some of the things. I have 3 bonus slides for you. First of all, I had this optimization here where I'm going to doing storing the reference in $station, so we don't have the hash map access. But the thing is, if the station already exists in the measurement already exists in the stations array, I'm going to do it twice, because for the is set and then here, he mentioned that we can obviously also do this in the beginning, and then just if the city doesn't exist, then the reference will be null, so we can check for null, which will be easier. We only do one hash map lookup, which should save something. That was like 2% less or something, I don't remember. So it was not that much, but I took it. It was faster a bit. This was also interesting. In the beginning, we had the exit condition was just that fgets returns null, because there is nothing to read anymore, and then we exit. And with the multi-threading, we basically have this chunk start and chunk end condition. So basically, this is the condition to end the loop. Now, because in the earlier function where we create the chunks, we already made sure that the chunks are aligned with the file itself. As long as we are in between those boundaries, we can read data. So we don't need to check on fgets. So basically, while the condition for the loop is just as long as we are in between chunk boundaries, we're going to read and assume that we got something because we defined the chunk borders earlier. So it's safe-ish to read. That's one thing. And another thing which brought the most performance improvement was this thing. I was reading using fgets and then adding the string length to the chunk start so we know where we are, then string pause, substring, and all of this dance. The problem with this is still it's a lot of string operations, a lot of memory operation. PHP is copying around a lot of strings and creating a lot of new data. And one of the things is we can read with fgets to the end of the line. But turns out there is a function that I wasn't aware of, that's stream getLine. And stream getLine, you can give it a file pointer, you can give it a hint of how much byte it should read. And then you can also give it the character where it should stop reading data. So stream getLine would stop not at the carriage return line feed, and then we have to split and do all the stands, but we can say it should stop at the carriage return at the semicolon and give this back into city, and then a second stream getLine call, which should stop at the carriage return line feed and give us the temperature. Then we have to do the string length dance again, but the string length are stored with the string in PHP, though that's simple, and then do the conversion to the floating temperature. And with these changes, these 3 different changes applied to the same thing, running the same script again, we are finally down to 12.7 seconds. That was pretty awesome, coming from 25 minutes. So there is 2 major takeaways from this thing. Basically, 25 minutes can totally be okay. If this is a one-time thing, like I mentioned already, developer time is expensive, CPU time is cheap. I would have not been mad at all if I would have run this and it took the entire night, because you just start the thing, the next day you have the problem solved, so what gives? And also it took just a few minutes to come up with something that solves the problem. So PHP is a quick language from that perspective as well. And even technically, if you face these challenges where you're like, we have the CPU-bound problem now, so we can't use PHP because we got to use Go or Java because all the other guys are doing this, and it's a CPU-bound, it's a heavy problem, PHP is not made for this. Well, PHP can solve those problems super quick. So, yeah. And yes, and PHP also has multi-threading support, so even multi-threading is not a thing that is a problem for PHP. With Xparallel and the CTS build of PHP, you have userland multi-threading and can spawn threads and can put CPU-bound workload into a background thread. And with that being said, thank you everyone for being here.
Ooh.